Hello, welcome to another edition of James and Chris Science Videos, where today we're going to be looking at density. We're going to look at the equation, we're going to look at the definition, and I've got a couple of little practicals that you can do at home in order to understand a little bit better the principles that we are going to discuss. So let's start with our kind of definition of what is density. And I'm going to start with a standard question that a lot of science teachers ask. And that is, which of those two objects is heavier, a kilogram of iron or a kilogram of feathers? And the answer, if you think about it, is that they're both the same mass, because a kilogram of iron weighs the same as a kilogram of feathers, or has the same mass, I should say, rather than weight. So that's not a fair question, because there are other factors that come into play when looking at materials than just what its mass is. So if I asked it a different way, if I said to you, which is heavier, 1 centimetre cubed of iron or 1 centimetre cubed of feathers, that becomes a fairer comparison. And in this case, the 1 centimetre of iron would be much heavier than 1 centimetre cubed of feathers. And it's this idea of equating mass in a set volume that describes what density is. It's the amount of matter in that set area, and in case of what we're going to use for our syllabus, the volume that we're going to use is 1 centimetre cubed. So we talk about the mass in 1 centimetre cubed. There is an equation that goes with this. So my equation is density equals mass divided by volume. I put the units in, grams divided by centimetres cubed. Grams per centimetre cubed is my density. Then I've got grams for mass. I've got centimetre cubed for volume. And again, it makes sense. If I've got 10 grams in 10 centimetres cubed, how much have I got in each centimetres cubed? Well, I'd divide the two together. I'd divide my 10 grams by the 10 centimetres cubed, and I'd work out that would be 1 gram in every centimetre cubed. And that gives me my comparison that I can use. So how many grams in 1 centimetre cubed? Now, how do we work out the density then? Well, practically, first thing we need to do is work out the mass, and the mass is easy. All you need to do to work out a mass is put it on a top-hand balance. The top-hand balance will give you its reading, and the reading in this case will be in grams. So we've got our mass. That is easy to do. The volume is going to require a bit more thinking. It depends what type of object we're looking at. The object I put on the screen at the moment is something that we call a regular object, a regular shape. That means it's going to have straight edges and it's going to be an easy to find volume. The equation that I need for the regular shapes is that to work out volume, we times the length by the width times the height. And that will give me the volume of that object. Now, not every object is a solid. Sometimes the object may be a liquid. This again is quite easy. To work out the volume of a liquid, we pour it into a measuring cylinder, and a measuring cylinder will tell us exactly how many centimetres cubed is taken up by the water. Now, a little note, 1 millilitre is the same as 1 centimetre cubed. They're the same value. Sometimes the object, though, is not regular. I've put a pebble here, and the pebble does not have regular sides. It's not easy to measure by the sides. We can't measure length, height, width. It's irregular. So we need a separate method for doing this. And to explain this method, I'm going to go to the lab and I'm going to show you a piece of equipment that we use in order to measure that pebble. The equipment I'm going to use is something called a Eureka cam. And I'll join you back here once you've seen how that works. Okay, so far in the topic we've learned how to measure the density of regular objects, where we take the mass and we divide it by the volume, and we've been dealing with volume irregular shapes. So we've been looking at timesing the height times the length times the width in order to get our volume, and then finding the mass using a scales and dividing the two to get our density. And that's very easy to do. Hopefully you've got the idea of that equation. Now, what do I do then if I'm given a shape that is irregular? It is not a regular shape. How can I work out the volume of this? So, and then therefore the density. So I'm going to need the two readings for this. I'm going to need the mass and I'm going to need the volume. The mass is very easy. Mass, all I do is I put it onto here, and so that's giving me a mass of 45 grams. 45 grams. The volume is a little bit more problematic because there is no length, height and width that we can use that is regular. So we want to find a different method of measuring the volume of this. And the method I'm going to use, I'm going to tell you the story of where it's allegedly, the legend of where it comes from. So this comes back into ancient Greek of a king called King Midas that was given a crown as a present. And he wasn't sure whether it was pure gold or whether they had done a metal with a gold over the top. And so he gave it to his top Greek philosopher, who was a man called Archimedes. And he asked Archimedes if he could tell if it was gold or not. And so the legend has it that Archimedes was very troubled by this, was threatened that if he didn't solve the problem, he would be expelled or killed. And he was really pondering it. And he got the idea of what to do when he went and sat in his bath. And he noticed that the bath was overfilled, and that when he got into the bath, the water overflowed and went out. And so therefore he could work out what the volume of the crown was, and if it was heavier, how that density could work out. So he could use the density of gold to work out whether the crown was pure gold or not. And legend is he jumped out the bath, shouted Eureka, and ran naked through the town. Now, I'm not going to do that, but excuse me, but the Eureka became the name used for the piece of equipment that we use to measure the volume of these. What I'm going to do, I'm going to show you how to use this device. It's very, very simple. What I'm going to do is take it up to here, and you fill the Eureka can with water. You go over it, and if you get over this point, you'll find that water drips out of the spout here. I then put a measuring cylinder underneath, and I drop the stone into the Eureka can. I'm going to let that finish dripping. Okay, there we go. So my volume of my stone, we can say the stone has displaced the water. It's moved the water out, and the same volume of water moves out as was the volume of the stone. So in this case, if we go up here, I reckon that is, what do you reckon, Mr. Kabats, 14?
14.
14. So the volume of the stone was 14 centimetres and the mass was 45 grams. So you should be able to work out using the equation what the density of this stone is. So that is measuring the density of irregular objects. Now, I do want to mention as well here that we can also use measuring cylinders to work out the density of water, because water and air both have densities too. So, same principle, it's going to be mass divided by volume. The volume of a liquid we measure using a measuring cylinder. That's how we work out the volume of a liquid. The mass we can do by putting onto some scales a measuring cylinder, zeroing it, and I'm going to fill this up with 100 centimetres of water. There we go, 100 centimetres of water. And I'm going to put this onto my scales, and the scales says 100 grams. It's actually 99, but I'm lying a little bit because I want it to make sense. So the density of water would be 100 divided by 100, which would give me a density of 1 gram per centimetre cubed. That's important because they use water as the standard that they use for the units. And so the reason it's 1 grams per centimetre cubed is because grams is based on water, and because centimetres cubed is based on water, and the whole lot is based on water. So you've seen how to use an Eureka can. Now we're going to put the figures that we took from that experiment into our equation, and we're going to work out the density of that stone in exactly the kind of way that they could ask in the exam. So what is the density of the stone shown in the video? Well, we know the mass of the stone because I put it onto the scales, and the top unbalance said that the mass of the stone was 45 grams. I then put it into the Eureka can. The volume of the water that came out was 14 centimeters cubed. So I put that into my equation. I then add it to my calculator, and the density of the stone was 3.21 grams. Easy to do. You find out the mass, you find out the volume, you divide them, and then you get your reading, which is your density. Be prepared to switch around your equation. Know how to move parts of the equation to the other side. So if I want to work out the mass, I would do density times volume. So you can move that around. Again, I'll do that on a separate video on how to manipulate equations and how to look at those. Part of the video also showed you that water has a density of 1 gram per centimetre cubed. This is quite useful because we can then judge if things and objects are going to float or sink. And the rule of thumb is very easy. If it is greater than 1 centimetre cubed, then it's going to sink. If the object has a density less than 1 centimetre cubed, it's going to float. And it actually floats by the percentage above what it is. So if I've got something that is 0.9 grams per centimetre, 90% of that object will be below water, 10% will be above water. The difference between the two densities will give us how much is sticking out of the water. Now, to prove this and to show this in action, I'm going to ask you to build a Cartesian diver. And a Cartesian diver is an object, a model that you can make quite easily in your kitchen, where you can alter the density of an object by squeezing on it. Now, I'm going to go to the kitchen now, and I'm going to show you how to make a Cartesian diver. See if you can make one, and then you can see how you can change the buoyancy by changing the density of the gas inside the object. So I'm going to leave you to do that, and I'll see you afterwards. Right, so now we're going to make a Cartesian diver. I'm going to show you the stages that you need to do in order to make this work. The equipment you need, you're going to need a straw of some kind. You're going to need either plasticine, I've got some blue tack. Play-Doh works, but it dissolves so it doesn't keep for very long. A pair of scissors, a plastic bottle with a lid, and a bowl of water are the equipment that you need. So the idea of this is to create, using the straw and plasticine, an object that has a density of about 1. So we call it neutral buoyancy. It just about floats. So what I'm going to do, I'm going to take the straw, I'm going to cut it, and we've got a bend there. I'm going to use my plasticine, in this case blue tack, and I'm just going to cover the end, and this will do two things. This will, first of all, keep the air trapped into the straw, so I've got the air there. So I just get rid of the dog. Out. Get out. Alright, there we go. So, here we go. We've got a straw with some air and some blue tack. We need to test this out by putting it into water. Now, if it sinks, well, that's pretty good. If it sinks, it's too heavy and you have to take some off. If it floats with lots of the straw sticking out, then it's not heavy enough. Now, you see that there just about floats. But I'm probably going to take, it's just a little bit too much on the edge. I'm going to take just a little bit of blue tack off and try that again. Not much, just that much. That should be. There we go, that's better. So it just about floats. You've got a little bit of the straw sticking out the end. Once you've done that, you need to put it into your bottle. And again, it should rise to the top. Tighten the top as much as you can and give it a squeeze. And when you squeeze it, it sinks to the bottom. And when you let go, it floats to the top. The reason it does this, inside that straw is air. When I squeeze on it, I increase the water pressure so the air bubble gets smaller. I decrease the volume of the air, and if I decrease the volume, it makes it more dense. So at the moment, its density is just below 1. If I squeeze it and I make that air bubble inside the straw smaller, I make the density more than 1, so it sinks. If I let go again, the air bubble expands and the density changes, and it now floats. Have a go making one of those, see if you can get the object to float and sink, and then see if you can explain it to your parents or to a brother or sister and tell them how it works. Stop. Great, so hopefully that worked and you've managed to show the straw rising and sinking when you put pressure onto the bottle to increase and decrease the volume of the gas. So let's summarize this lesson. What have we looked at? We've seen density is how much mass there is in 1 centimetre cubed. So when you think of density, you've got to think of every object into little cubes of 1 centimetre. The equation is density equals mass divided by volume. You need to know that. You need to learn it, you need to memorize it, and so that if they ask the question, describe the relationship between density, mass and volume, you immediately say density equals mass divided by volume. There are different ways of measuring the volume of an object. We've looked at regular shapes, irregular shapes, liquids, and gases will always take the shape of the container, so it's really the container that you're measuring, and that should be a regular object. Water has a density of 1, and that's important for judging if something's going to float or sink. I have put here under the correct conditions. That is true. If I heat water up, its volume increases and therefore its density changes. So there are some set conditions that water will have that density of 1, which is roughly, I think, 20 degrees Celsius and 1 atmosphere. So there we go. Hopefully you enjoyed that. Hopefully your Cartesian divers worked, and I hope to see you again soon. Thank you very much. Bye-bye.